speaker this evening has over 15 years of industry experience, was previously an Oracle DBA for Amdocs, as well as a senior database professional at Cisco. Please welcome the co-founder and COO of DBSH, Michael Elkin.
Hello everyone, thank you very much for being here. Together with me, David Chains, who will open this session, my colleague, and Hayam. This is something that we prepared to the end.
Okay, so hi everyone. I'm going to be the opening act after the opening act. So I'm David Chains, and we'll save Michael for just a few minutes from now. Before we get started, show of hands, sort of not no swag here. Who here works for an enterprise or works with enterprise? You know, banks, insurance companies, hospitals, whatever. Good. Okay. Who here has got Oracle databases, DB2s that they're working with? Fantastic. And who here is working with any Hadoop, NoSQL initiatives? Good stuff. Okay, great. So that's what we're going to get. Hopefully today you're going to find things are going to be pretty interesting. I'm not sure if you can see this well enough, but we are talking about getting our 70s guide together with our 2019 free spirit to see how we can make that work together. So we talk about the way the world is today. We still have your traditional databases, your SQL databases. They're not going anywhere. Your core systems, especially in enterprises, are running the key business, the core functionality of the organization. But on the other hand, you're very interested in taking advantage of new technologies. Okay, but what that does is it creates data islands. It creates disconnects and makes projects very difficult to achieve ROI. So traditionally, the way you move the information from one environment to the other is through ETL, product of the 70s. And it's what you do to go from your system of record to your systems of whatever's, analytics and new applications, offloading from existing core systems, which are expensive, to new environments, taking advantage of new technologies. Increasingly, what you're seeing is that we are looking at use cases now that are increasingly not big data, but they're fast data. You need the information to be there, up to date, right now, and you can't wait for overnight or for a few hours from now to do that. And when you get to those kinds of use cases, ETL just isn't good enough. ETL has got delayed delivery. They still are stressing your core system. You're doing selects, you're adding columns, you're doing triggers, you're doing things that require you to touch the core system. And these systems are high cost and very highly complex. So that's a problem for achieving real-time use cases. So at DBSH, when we looked at this problem, there are others out there, and we can address that later, not when we're being recorded. But the idea is we wanted to come up with a solution, and what we're discussing, this is not a sales pitch, so we're going to be talking about the concept today. But the idea is you want technology that is real-time. You want technology that is going to be non-intrusive. It's not going to impact your source. You need it to be simple. You want to be able to take it out of the hands of your DBAs. You want to take it out of the hands of the IT if they're just too busy and they want to protect the source. You want to be able to take that out of their hands and let the application team. You want the people that are creating the business logic also be able to manage getting the data into the business logic. And of course, if it's not enterprise grade, it's not going to be worthwhile in any real production kind of environment. Okay? This is what you're needing. If you think about it, it's not only on-prem, it's also on-prem, but it's also streaming to the cloud. Okay, so the idea is that you want to be able to take from multiple databases. You may want to be able to create a 360-degree view of the customer from multiple different databases. You may want to be able to offload processing from your core systems because it's expensive to develop new functionality on top of a mainframe DB2 system. Okay, you want to be able to stream this into some uniform format, and you want to put it into a data lake using some technology that's standard, that's out there, whether it's Elasticsearch or Hadoop or MongoDB or even graph databases. You want to be able to stream that in there in real time, or you want to be able to stream it to the cloud. Okay, so those are the kinds of things you need to be able to do today to help organizations modernize without revolutionize. If you're going to have to do a revolutionary rewriting of your core system, it's not going to happen. It's just too scary. So what you want to do is to be able to gradually move it out so the data is there and you can put new business logic around it. Okay? So then you start using things like the marketplace. You want to be able to make it easy. You want to be able to go out to AWS Marketplace, GCP, Azure, and be able to download it, configure it, and let it run. Okay? So one other thing, of course, is hybrid cloud, and there's also multi-clouds. So you want to be able to stream from an AWS to an Azure. Because whatever reasons you want to do that, it may be resilience, it may be just distributing the load, you need to be able to move the data. It's got to democratize the data and make it available to your application people to be able to do with it what they need to do and not what the IT organization has approved. Sorry, all those people in the IT organizations here, I apologize. That's the scene. That's the problem that we like to talk about this evening. We have a surprise. We've already sort of revealed the surprise, but we're going to let Michael now take over the reins and actually walk you through and get a little bit further down into the details. And then we're going to ask Kayam to come up and give his real-world example of what's being done in a real, very interesting case. Okay, thanks very much. I'll hand it over to Michael.
Thank you, David. Thank you very much. So my name is Michael Elkin. I'm co-founder of DBS-H and technical lead. Thank you very much for being here this evening. And it's great for Eric that organized this event. Nice to see such a warm database community in New York. We are from Jerusalem, and it's great to see our community sharing information. So I would like to deep dive a little bit more in streaming, and I will start with a core architecture of the SQL to NoSQL streaming that in our case is based on CDC, transaction load mining. And in this slide you can see an example of Oracle that we capture transactions directly in real time from read logs or archive files. People here work with Oracle, so I believe that you know the concept of transaction log files. And after that, we transform from the raw proprietary formats that Oracle has at SQL Server or DB2 or mainframe. We do support DB2 and mainframe as well, into open JSON format that can be pushed to many targets. And we will talk about these targets a little bit later. But the idea is to run something that can capture in real time changes without installing any agent on a source database. All the source database or the legacy database today, they are very sensitive for anything that you will install and you will add additional load. So we created an engine that can run in a dedicated VM in the cloud on a physical server that connects to the source database like any other Java application and reads directly transaction from transaction log files, read log files, archive files, and then all the processing, parsing, transformation to H-based format, to Kafka format, to Neo4j format is done outside, and then we push this transaction to the target. So the existing applications continue to use the legacy databases as is. It is not required to add anything like new column with time-based or to create some triggers in order to capture new changes or stuff like that. It's completely transparent to what already is running and updating existing legacy databases. We are talking about Oracle, of course. We support Oracle starting from 10G version, even before. We support Oracle real application clusters, reading transactions from archive files on ASM, on a proprietary Oracle file system. Even Oracle 12c with container databases if you started to work with. Of course, SQL Server, DB2, Ingress, Amazon RDS. By the way, someone has started to use Amazon RDS, Oracle RDS here? Okay, great. So our engine is capable to capture changes from Amazon RDS transaction log files. And if you are looking for kind of solution of multi-region replication or multi-cloud replication between Amazon, Oracle RDS to somewhere, in Azure or GCP or another region in Amazon, it can be a great fit. And from the target point of view, our main focus was the new world of NoSQL engines and big data. So in a Hadoop platform, we do support pushing and publishing changes in real time to HDFS, to HBase, Hive, Kafka, of course. We support MongoDB. It was the first engine that we added as our target. Amazon RDS, any SQL target, starting from Postgres, Azure SQL, SQL Server, and Oracle target, of course. Google BigQuery, a very interesting target if you look at any Java message queue or message bus, can be used as a target, and more. And we add new targets actually every day. So I think that the best way to explain how it works and different scenarios and different use cases will be through the demo. So I will move to the demo. The demo is very, very simple. It is based on a single source. With the same transaction, we will go through the demo and you'll see the same transaction is published or pushed to different targets. And how it looks like in graph database, and let's say Amazon S3 or in MongoDB. And in Elasticsearch. This is what we will see today in the demo. As a source, we choose Oracle database with this very simple schema. 3 tables, customers, products, and orders. You know, it's a very simple, but you have primary foreign key constraints, some relations here. So we will see how we translate a relational databases with relations in the form of referential constraints into, let's say, graph database where the concept of relation is very deep, and you have to understand how you map existing relational database into the graph database, and etc. So this is how our demo looks like today. We choose to show you Elastic, Amazon S3, Neo4j, and MongoDB. So I will switch to the demo. Good. Okay. Currently, what we have here, I'm connected to the Oracle database, so SQL developer. We have these 3 tables: customer, products, and orders. And we have this customer number 59. So when I fetch the data from customer number 59, I got this information. Like customer city, address, and private data, etc., etc. So as a first step, I will show you MongoDB as an optional way of actually replicating directly from SQL sources to MongoDB, keeping exactly the same structure. It can be very useful in different use cases where you would like to have a reference data in engine like MongoDB instead of going back to your legacy databases that can be Oracle or SQL Server for different purposes, but you don't want to go back every time to query, let's say, customer information or product information. You would like to have it inside your data lake or data mart, new data mart that is built on top of MongoDB. So CR8 is capable to do an initial sync, kind of dump from the source, SQL source, to NoSQL target. So in this case, you will find in MongoDB the same structure. So it's a very simple case, very similar to what you know already from any replication tool that does the same. So we are capable to do the initial full sync and then starting capturing changes from the exact point of the full sync, and from reader logs, and so on and so on. So if I will go back and run a simple update, currently the credit limit field is 67,000 in MongoDB. I believe. Can you see that? Or
We trust you.
or you believe me? Yeah, I think you do. And let's update the credit limit. Let's raise it by 1,000 and run a simple update with commit. Okay? So right now, if we run a query in MongoDB, the credit limit is 68,000. So in real time, what happened, we captured the transaction and run an update command on MongoDB. Because the structure is the same, and MongoDB is completely schemaless design, it is relatively easy to achieve. But this form of streaming data to NoSQL is a basic one, and we have different forms that we call journal mode. So in journal mode, we understand that you not necessarily always want to see your data like this, like an exact replica of your source. Sometimes you would like to see your transactions in a form of a journal entries that allow you to actually to track and trace the evolution of the change. So what we do, we capture every transaction, every command, insert, update, delete. We can capture DDLs as well. I mean, create table, add column, stuff like that. And convert it to the insert statement into the target. When you have a metadata section about the original transaction, like what was the time of transaction, what was the source database, what was the source schema, what was the source table, and so on, and the metadata can be expanded with all values and all columns with the new values and all columns with previous values. So you always can compare, find the fields that were changed, and actually involve some application and business logic for transformations. The journal format is very popular when you use a target as Kafka, for example. You can think about this JSON document as a message. So every transaction, actually every command that can be that can include multiple one transaction can include multiple commands. So every command is transformed into the message with metadata about the original transaction and all the new and old values. When you use Kafka and then you create your consumers to consume these messages from Kafka, you can always run enrichment, you can always run transformations, and actually accept streams from different sources. By the way, we implemented the journal mode streaming not only to MongoDB, that is very flexible and schemaless, but to Postgres as well. So you can stream from different operational databases, different oracles, when you have this exactly the same structure in all of them, into the single table. Let's say you have customers table in 20 Oracle sources. So how you can capture all transactions from all of them together into the same customers table on a target using the journal format. Using the journal format, you will have for every record identifier from where this transaction came from what database, from what schema, and then you can know, okay, from one region I have this insert, from another region I have this update, even though all of them have identical structure. This is a journal format. So the next slide that I would like, actually the next part of the demo is focusing on Neo4j. I have a question. Someone here started to work with Neo4j or any other graph database? One? Okay, two. Good. So Neo4j or any graph databases were developed, actually it is an extension, or we will call it an evolution of relational database. In a relational database today, we define some primary keys, foreign keys, but it may need to maintain integrity. Like I cannot submit any order before I already have a customer or a product, right? But there is no business logic, actual business logic between these entities. We have many-to-many relations in a relational database, but it may need to connect like tables with customer and orders. In graph database, it's an evolution, they call it an evolution of existing relational database when the relation itself plays not only the role of kind of constraint or enforcement of the database, but it plays a major role as a database object. Means that you can, for example, design your business entities in a certain way and define how these entities are related, what are relation between them. So when we translate the relational database, so we try to build the new graph database based on existing operational systems, this relational database, there is always the first question, okay, how we map the existing picture of my relational constraints into the new world of graph database. So if I run a query on Neo4j right now, and we will increase and zoom out a little bit, this is how this small database with customer products and orders looks like in a graph database. This is a small graph with relations. There are many graphical tools that can present you graph database differently. This one comes with Neo4j by default. Green nodes here are customers, blue nodes are products, and the relation here is actual order. Who defined a schema in Neo4j this way? It's up to you. So maybe your design in a graph database will be different, and order will be the main object, and product will be the relation. It depends on the business logic, on a use case that you're trying to resolve. But we provide a mapping interface where you can map the existing tables to relations or to nodes. And when you run an insert, update, or delete an oracle, the engine behind the scene knows how to transform this insert into Neo4j, or to create a new relation, or to create a new node, or to find two nodes and do something with the relation between them. This is how it works with Neo4j. So if we go right now and run a query of this particular customer, we'll look for all the relations of the customer number 59. This is the customers that we are working with. So currently you see Austin purchased a jacket, right? This is what we have. When we update something in Oracle database, we have a lot of information in this update, right? We have a last update kind of purchase timestamp, what was the purchase amount, and stuff like that. So when it goes in a relational, in a Neo4j database, it goes or on the node level as an attribute, or on the relation level as an attribute. So you're free to choose what will be shown as the main label of every node, and what the metadata will be pushed to the node itself or to the relation itself. So you do not lose any data from your original relational database when you stream the information into the graph database. So if we go and create a new order for this customer, is let's say this is a PL SQL procedure that generates a new order for customer 59. Okay, so the new order number is 807, and if we go and run the same query again, you will see it is another jacket, but it is a second purchase of this particular customer. So what happens right now? In real time, the same engine captured this another change. Actually, it was an insert statement, and published it to the graph database. On the fly, the new node of product has been created, and the relation, actually is the link between the customer and this new product has been created as well, including all the metadata that has been found in the original readable record. I mean, what was the timestamp of the purchase, what was the amount, and everything. So we don't lose any data. Everything is published to the graph database. The next example that I will show is actually Amazon S3. Amazon S3 is a very interesting use case where, first of all, you can think about it as a file system, but it's an object store. It's a not normal, let's say, Linux file system. It's an object store, and every file is represented as an object. So in our case, what we do, we capture changes on source and then publish them to Amazon S3 when every transaction is an object in Amazon S3. What you can do with this, on the basic level, you can think about audit trail, right? Very cheap and affordable audit trail for anything that is running right now in your database. Of course, you can filter at the beginning and say, okay, I don't want to audit all my tables. I would like to audit only 10 of them for particular commands. Let's say only for deletes on the critical tables. And then publish it to S3. S3 can serve you as a great backup area for transactions, or area as the first, let's say, stage of the data mart for analytical processing. On top of that, you can run Spark jobs, consumers, and stuff like that. So if we will look at this file, and I'm using right now a nice feature of Amazon that allows us to actually to parse any JSON file and present it to us using Amazon Athena. So it's a SQL-based interface on top of Amazon S3. It's very useful. You can actually, because the JSON format is recognizable by Amazon Athena, you can actually create SQL statements and run SQL statements on top of all the files and all the changes that were published to Amazon S3. And this is the result. As you can see, it is very similar to what you saw already in a JSON format in MongoDB. You have a metadata. You have a metadata of the change, the schema name, the table name, what was the timestamp of the change, and then you have all the changes. In our case, it was a new order number 807. This is a new insert that has been captured and pushed to S3. And the last thing in my demo, I will show you is the Elasticsearch. Elasticsearch can be a very interesting target and NoSQL target to capture all my transactions and push them into Elasticsearch. Someone has an experience with Elasticsearch here? Full text search? Okay, great. So Elasticsearch is another very popular engine today that behind the scene it actually uses open source Lucene full text search engine that does a very smart indexing algorithms that allows to search, to do a free text search on any text. In our case, we capture changes from relational databases and transform everything actually in text. Because the JSON document, in the end, it's a textual file. So if you think about a relational table that has very well-defined fields like customer name, customer address, and everything, and suddenly you find there notes, comments, and usually it comes with some kind of huge glob XML inside, and there's a lot of very valuable information there. How can you search? Oracle gives us some tools to search through clubs, but if you don't know the structure of the club, that is particular XML, if you don't know what fields to search inside, it's become to be very, very difficult to run sophisticated queries on semi-structured or unstructured columns inside your relational database. In this case, what we do, we capture the original transaction, convert everything into the JSON, standard JSON format text, and publish it to Elasticsearch. Elasticsearch has a smart indexing processing for everything, so even without knowing the field name, you can search, for example, for the word service, like here, and find all the transactions where the word service was included. It can be in some nodes column, some inner XML, or it can be in some very well-defined column, like how this purchase has been performed through the call, online call, or stuff like that. So Elasticsearch can be very interesting target for any streaming use case from Oracle, SQL Server, to do a free text search and analysis on all the transactions that are running on a source database. This is all for my demo. I will go to the next part of my presentation of lessons learned, and I think we do have time. We have a time for questions in the end, so if you have right now questions, remember them. Do not forget until we have finished this session. So we run different use cases, different streaming use cases in different customers, fields, and sites. And I choose actually 3 or 4 with different tips and lessons learned. And the first I'd like to start with is Kafka. So Kafka as a target is, I think, is the fastest choice for streaming from relational databases, from existing legacy databases like Oracle, SQL Server, to anywhere. Because of the nature of Kafka is built for streaming. Of course, there are a lot of work to do after the information landed to the Kafka. You have to consume it, you have to transform it, you have to write your own Spark jobs, for example. But if you would like to get it as fast as possible, and you have a very, very heavy loads on your source, Kafka is the best choice. But still, you may have a very loaded source systems. So how you stream, and you do, we call it ultra-fast streaming to Kafka, without impacting your source. And this is a critical part of any streaming, that your Oracle database that was tuned with all these indexes and all these parameters that we all know will not slow down because of some streaming agent that right now is streaming changes to Kafka, to new big data lake initiative. So we learned that there is an option to stream, and this is very efficient if you can afford from application side, I mean from big data application side, to get changes before they were committed. There is an option to stream from transaction log files without waiting for commit, actually. The work should be done on your consumer side, because if transaction has been rolled back, you have to do something with this information after that, when the transaction is replayed. The next thing is to work with Kafka partitions. Kafka itself is a very, very efficient engine, but if you stream a lot of, almost all your volume of the source, or from many sources, into the same Kafka cluster, it slows down. So you have to plan and split into different partitions efficiently, then it can help in the Kafka performance. there's an option, it depends on your use case, but sometimes you can be only interested in new values. I mean, if you run an update and you are interested only in what has been updated, without the need actually to consume the old values of the record, you can omit this part, and this significantly reduces the amount of data pushed to the Kafka. And the network between the engine and the Kafka sometimes is very, very critical, especially on a high throughput and high load. So we come to the situation when we work even without ACKs. We do not wait for acknowledgement from Kafka, and we publish as we read from Oracle in order to make the streaming faster as possible. And Kafka batches, of course. HBase. HBase is another very popular use case that we deployed in the field. HBase mistakenly many times considered as a database. It is not. It is not a Hadoop database or Hadoop relational database. HBase can be used, and sometimes it looks like a relational database, but it is not. You have columns, you have column families, but what is important is that every record is a very well defined row key. And the definition of the row key is critical when you plan your HBase, and when you plan the streaming from your Oracle tables to HBase, it can be, of course, your primary key that can be composed from multiple columns. Then you have to plan how you create this row key in HBase, but it can be something different. The tricky part here is that if you decide to change after your HBase is created, it's very, very difficult. Row key cannot be changed. You cannot have different row keys for the same HBase table. So the design of the HBase row key is critical, and especially when we stream from already existing relational database, relational tables to HBase. Row key can be, of course, the mirror of your primary key or unique key. Can be composed from different columns. So if sometimes it's very useful to define kind of delimiter. HBase performance. From streaming point of view, Kafka is much faster than HBase. But in HBase, you do have logging mechanisms, very similar to relational databases. So it's called write-ahead logging. So you can play with it. If the streaming is not fast enough, you can turn it to asynchronous mode instead of synchronous mode. And if you would like to avoid it completely, you can turn it off. I wouldn't recommend to work completely without write-ahead logging in HBase. Only in cases when you have a full dump, kind of initial full sync, that the idea is to load as much as possible, huge amount of information, like all your tables that may several terabytes of data. So in this particular use case, you can work with skip write-ahead logging in HBase and then turn it back. And high. What we do usually, we understand that working with HBase out of the box can be difficult. It is not SQL-based database. HBase by default, they do not provide SQL interface. So what we do, we build on top of HBase Hive external tables, similar to Oracle external tables, if you know what I'm talking about. So when you have Hive external tables on top of HBase, you can run SQL interface, SQL queries on HBase, and it helps a lot. And you got feeling like you stream from existing Oracle or SQL Server databases, and you're still working in a known way using SQL interface, SQL language. Additional interesting thing with HBase doesn't have secondary indexes. I mean, you create a single index on a row key of HBase, and if you'd like to have a different index on something else, there is no such a feature out of the box in HBase. So what we understand that when you stream something from Oracle to HBase, of course, you have a lot of searches and queries based on the primary key that can be your raw key in HBase, but maybe you have another index in Oracle. So how do you achieve this in HBase? We can, so through CRA, you can do this mapping and create secondary indexes. It is implemented in a way of additional HBase tables, like lookup tables. But at the end, you can search by different columns, by different keys, even in HBase. And all this in real time, and the real-time streaming, it goes from Oracle into HBase. HBase conflict resolution is a very, very tricky part. Actually, any conflict resolution in a streaming or data integration or replication flows is very, very difficult. Because if a streaming engine or CDC engine tries to update something, and on the target there is a different record, it is an error. So what we did, we understood that a target is always open for reads and writes. So our target HBase MongoDB can be updated by something else. And we can get out of sync. So what we can do, we don't want to stop streaming. We don't want to slow down. So we implemented internal conflict resolution. Means that always the source is always right. So if we try to do some update and we find something different, we just delete this record and create the new one. The same is deletes, the same is inserts, and stuff like that. It is performed, it is not a new concept. In relational databases, the conflict resolution of bidirectional replication was always there. In NoSQL world, it's something new. And this is what we implemented. Internal conflict resolution for insert, update, deletes. The last thing is HBase. HBase by default marks every record with a timestamp. The timestamp granularity is milliseconds. As you know, in Oracle, you can run several commands even in the same millisecond. So in this case, you're running into some kind of race condition in HBase that you cannot. Actually, HBase doesn't throw any error in this case. It just gets some. If you send 3 commands, it will take one of them without any actually order. So you can find a different solution. Actually, overriding the default mechanism of timestamp in HBase, but this is something that should be taken into account when you're working with HBase, that if you have a very heavy loaded source database, you may run into this timestamp issue with HBase. Few lessons from graph databases. Many-to-many relations can be implemented through, usually you have 2 tables and the third table that actually connects many-to-many. In relational, in graph database, it can be a relation, but you have to map how you map your original source tables into graph entities. And you can, through CRA, we provide a mapping mechanism where you can say, okay, this table actually a connector between 2 business entities, between 2 tables, and this table will serve as a relation or only as a connector. The dynamic labeling. The labeling is critical in relational graph databases because when you see a picture of the graph, like we saw a few minutes ago, it's very important what you present. On the nodes, on the labels, then your analysis goes in the wrong way if you present different labels. So what will be presented as a primary label on the graph database can be mapped through the same mapping interface, and then automatically correct labels will be presented in the graph. In Elasticsearch, what we found that having a complex structure, that we have this complex JSON with embedded documents and everything, sometimes can be very problematic. Elasticsearch assumes it can work with JSON files, it can work with different types of files, but for JSON, it assumes a flat format, means one level of JSON without going with embedding documents and inner levels. Otherwise, Elasticsearch just will skip and will not index inner documents, and then you can search. It becomes to be a part of JSON that is not searchable. Then there is an option to convert complex JSON structure into the flat format and then publish it into the Elasticsearch. So if you're working with the streaming engines, it's better to have a flat output into the Elastic. This is all from my side, and right now I would like. Yeah?
Thank you, Michael. We have hand for Michael, please. So what I'd like to do is introduce Kenichi. Kayam is a Senior Vice President of Big Data Architecture Engineering at City TTS. And we're very privileged to be able to have him stand and present the implementation and his experience in general with the with this data lake implementation that CRA is part of. But the idea, of course, is for you to get an idea of end-to-end what's being done. So we'll get it wired up, and then we'll just kind of tell you about it. Thank you very much.
Okay. Oh, great. Can I do some more? Great. So sorry, you have to excuse me a little bit. I have this intermittent cough that kicks in. Last week I had a co-worker who was coughing all week, and suddenly from Monday I suddenly developed the same thing. The brandy was very good, but it doesn't seem to solve the symptoms right just yet. I'll probably need another one after the session. So my name is Kenichi. I head up the big data platform at Citi for Treasury and Trade Solutions, which is a division within Citi. Citi is a huge organization. I'll give you a quick overview of what my division does in Citi, and then really lead on to the use case in terms of how we used CR8 to really enable streaming and really a real-time use case for us based on our tech stack and based on sort of our huge inventory and ecosystem of existing sort of legacy databases. So we'll get a bit into that. So TTS is a global business. We're part of what's called an institutional client group. So you have within Citi, you probably have seen the retail branches, that's the consumer side. And then there's an institutional side for sort of corporate businesses. So this is really for corporate multinational companies, for other financial institutions. We operate in 160 countries. We're in 98 and we do business in 160 countries worldwide, primarily for cash management. So you're talking about making payments, receiving payments, doing liquidity management, commercial credit cards, doing working capital, those kind of services. So if you think of something like, and we have most of the Fortune 500 global clients. So Google, your Amazons, Uber. If you think about Uber drivers, when Uber has to pay them, they go through the Citi network in essence. So they come, in the part you'll see the use case that we're talking about in terms of how our big data implementation and then how we use CRA to enable some of that work to be done. So that's a quick high level of what we do in the TTS area. And we'll talk a bit about now getting into the use case. So for us, payments is a very large part of our business in terms of making payments to people, for organizations, to both customers and third parties. So when you make a payment, if you think about a payment in a traditional sense, it can actually be quite a complex process.
given cross-border environments, different countries, different regulations, different types of payments. So within the US, you might have heard of ACH payments, we do wire transfers. If you go into the European Union, you have a different type of payment system called SEPA payments. There's different types of payments. There's low-value payments, high-value payments. So with all that, what would typically happen is a customer, sort of a corporate client, would put in a batch of payments. They have a portal to do that. That payment would then go off through this life cycle of payment. It would get validated. There would be a credit check. There would be a balance check. There's sanctions checks involved to make sure that you're not, a bad person. The beneficiary, the person you're sending that payment to, isn't on some government checklist. So there's a whole slew of processes that happen for that payment, and then for the end payment to actually be sent outside of Citi for clearing, gets cleared, gets deposited in the final beneficiary bank account, right? So that, if that payment was initiated, it would be received, but from a Citi portal perspective, for that person to see it, they would only see that payment once it's been processed and it's been processed by the beneficiary bank and they've received it. If something happened to that payment in between, like if any of these issues occurred, or they were on a sanctions list, or they didn't have funds, they would have to ring up. They would have to call up the service center, and it could take anywhere from between an hour for a happy use case where they would know they'd be able to track the payment, whereas a more complex payment that's going to a foreign country, maybe somewhere in Azerbaijan, you could take up to 48 hours to get your status back on where your payment is. Right? So that was a big problem from a business perspective that we had to solve. And now the problem that we have is that Citi, like most banks and most financial institutions, they've grown organically, they've acquired other companies. So you have other systems, legacy databases, vendor products, regional products, country-based, regional-based, and then global-based. They all operate in different technologies, right? Different technology stacks. So in order for us to do this quickly and rapidly, I think as Michael and David were mentioning, we couldn't re-architect the whole ecosystem. Right? So we couldn't go in and say, okay, we're going to have a standardized database and a standardized connectors across the whole sort of payments process flow. So in essence, what we have to say is, okay, we'll use the existing databases we have, and then let's see how we can read that data, be able to replicate that data in real time, put it into a standardized format that everyone understands. So in this sense, what we're talking about here is based on industry formats. There's what's known as a CAM-T52, which is an industry format of an account and a payment. We wanted to standardize what a payment looks like, because what will happen is you go to one payment system versus another payment system, and within their databases, obviously the idea of a payment is totally different. They'll have a totally physical architecture, even a logical architecture will be different. So we wanted to standardize what a payment looks like. And once we've done that, we then have a common form of a target, of what target looks like. So we can now replicate and transform in real time, near real time, transform to a common standard format, and then present that format downstream to whoever the consumers are. So in this case, you can see there's a portal. So that was the idea, and that was the vision in terms of what we wanted to do in terms of the business problem that we wanted to achieve. So from a business perspective, it was really clients and customers wanted to see everything real time as possible, get their information, have a globally consistent view across all countries, across all boundaries, regions, whether you're in Europe, whether you're in Asia, whether you're in Latin America, and then have a standardized way of presenting that information to them. Right? So that was kind of the aim of what we had to do. So to meet that, what we did, we had to think a bit outside the box, and we kind of collided into DBSH actually. We were going down this path of CDC, using change data capture to really expose and unbundle our traditional database, right? Because we wanted to take it out of those monolithic databases, because we've got very different types of databases. Being Citi, we've got a huge legacy platform set, so you've got your Oracles, we've got Sybase, we've got SQL Server, we've got DB2 on AIX, we've got DB2 on mainframe. We've even got some Fox Pro apparently still running around. So there's very many different types of databases. Right? So the whole point here was, let's unbundle that database. So we looked at replication technologies. We did a whole sort of pilot case study around that. And then we met DBSH and walked through their solution. And what was really appealing was the fact that we didn't have to, we couldn't be intrusive, because a lot of these are in-country systems. We don't have the mandate to go out and actually change them or impose agents on their servers, etc. So the whole point here was that CR8 runs remotely. It doesn't run on the actual database or your source system. So we're able to run this remotely. It could be in a VM, it could be on physical hardware. And it's non-intrusive in that sense. It's really just reading the redo logs, the archive logs from the underlying database. So we were able to set out a design, an architecture using CR8 as our CDC tool, and really then designing a pipeline downstream. So once I've got CR8, the good thing with CR8 is, as you've seen, there's many different targets. So for us, what made sense was we didn't want to replicate one-to-one, given the fact that we had to standardize. We have many different types of payment databases and applications, and we wanted to standardize in a common format. So what really made sense for us was to use Kafka. Kafka to standardize and then process after we've received the core database event. So CR8 is great in sending you those events to Kafka, and then once you've got them in Kafka gives you you then have that flexibility to do what you want with it. So then you can process that data, standardize that data, enrich it, and then push it downstream. So that's basically what we ended up doing. So this diagram may be a bit, I don't know if it's hard to read, but I'll quickly walk through sort of from left to right. So source systems wide, we have on the left-hand side, you see all these are all the kind of legacy databases. You've got your oracles, you've got your Sybases, SQL servers. And essentially CR8 is now listening to those, it's using a JDBC connection, it's listening to those reading logs, it's listening to those archive logs, it's picking up all those database events in real time, pushing it to Kafka. Once it comes to Kafka, what we've done is we have different topics set up for different source databases, and from there we have basically we're using Spark streaming. So Spark streaming is then essentially doing the sort of core ETL, if you will, but in a real time on a real time batch windowed basis, right? So it's basically splitting up micro batches. But in essence, we're able to take that data, transform it using Spark streaming. We then push it into HBase. So Michael again, mentioned HBase. So we use HBase as a target. We do further manipulation within HBase as well. And then what we do is, at the same time as we do that, once that's done, we also put it into, we have a caching layer, because remember, this has to be used by clients pretty much on an online portal in real time. So the idea here is that while HBase is very good for processing the data and doing large volumes of processing and storing that data, we needed certain flexibility, as was mentioned. HBase is a single row key-based database. You can't do, if a customer comes in and he wants to do a slice and dice or a sort on his payments, look up the value date, look up different information, filter that data, that's hard to achieve in HBase. So what we're using is really a version of Apache Ignite, which is an in-memory distributed cache. Vendor supported, the product is actually called Pregame, and we're using that to keep the core payments then in memory. And then those are being exposed through an API. So we have a RESTful API service layer that then talks to our enterprise portal, CityDirect, which is then used, it's our customer-facing portal where queries and these queries and searches come in, and then we're able to satisfy those through the API. So at a high level, that's kind of the flow. So we use CR8 in a real-time ingestion mode from all these legacy databases, split throughout the world, and then they come into our cluster, into our Hadoop cluster, where we're running Kafka, and then from Kafka we Spark stream, do ETL, enrich the data set, pass it down, push it down to HBase, push it into the cache, and then it's available for end users. So that's kind of a high level of the architecture of how we're using CR8 to really give us that real-time streaming capability for a lot of these legacy databases, and to really unify our payments, right, as we push out the payments and are able to give that insight back to our clients and customers. So in terms of some considerations, we went along this journey with DBSH in terms of how we structured this and do this. So, and I think Michael touched upon some of this in his learnings as well. But really, you have to use Kafka partitioning to your kind of strengths. It's really a key factor in giving you parallelism. We had a set number of partitions that were created. We used a hash partition key to randomly distribute between those partitions to give us parallelism and throughput. We were using just regular Spark streaming, so basically based on the DStream API, so it's micro-batching. It's micro-batching those events. And we're now enhancing that with some of the new features in structured streaming that come out this year, so that you get more of an unbounded view of the stream, and you depend on the end of the stream. So there's some changes we're making to that. But right now, it basically operates as a micro-batch based on a time window, and then it takes that data set and is able to stream that, make operations on it, enrich that data. So what we're essentially doing is, if you think about payment, we're standardizing things like the payment status. So has the payment status been received? Has it been acknowledged? Has it gone through validation? Has it gone through sanctions check? All the different systems give us different values, and we standardize that into an ISO international standards-based enrichment. So we standardize those, we enrich certain fields, etc. And then we push that down into HBase. In HBase, I think, as Michael mentioned, from a time dimension, from a time stack dimension, once you put into HBase, it goes on a millisecond. Timestamp is based on a millisecond. Now, when you're getting millions of events coming in, that can be a problem, right? The other part is, if you think about this problem, what you're doing is you're taking stateful events from a database, and you're putting them through sort of what wants to be a stateless process from a streaming perspective, right? So you can have out of order events coming through. So the way we handled that was to in CR8, what happens is when you get that JSON message, it actually includes the command SCN. So that's in Oracle. If you're familiar with Oracle, the SCN is the unique way to identify each and every transaction record event within the database. So we use that command SCN that's passed on from the message, and then we use that to actually push down into HBase, replacing the timestamp. So now everything is ordered by your SCN. So events can come in out of order from a streaming perspective, but now HBase is automatically ordering that by the SCN, so everything's in order in terms of updates and inserts. So that takes care of really making sure that your ordering is correct on the target, even though you put it through sort of a streaming process, and you're getting stateful transactions from the source. So took care of that. There's other factors in terms of just tweaking the way your batches operate, how many dynamic executors you have within Spark. Spark has a lot of parameters and variables there that you have to kind of fine-tune in terms of the performance of the batch and how it operates. From a Kafka perspective, the offsets and being able to replay events is kind of key for us in having a repeatable process. So if we have an error in a payment, or we have an issue, we can replay that individual payment based on the offset. We have an offset tracker that we keep. So we've tried to make this sort of resilient as possible. The actual, from a Kafka perspective, everything, you have a leader and follower, which elects which partitions you use, so that's all backed up. And then within HBase, you have our concept of region servers, which are also multi-replicated throughout the cluster. So we ensure that we have resiliency from that perspective. So those were some of the learnings, but that's kind of a high-level architecture of our use case of how we implemented using CR8, and we were able to basically take those legacy databases and take that information and then consolidate and present back to our users in real time. So we're currently running, we have about 50 plus source databases that are being read by CR8 in real time. Roughly on average, we're processing around 2 million database events in an hour on any one of our topics. And then that's being processed in real time through streaming to HBase and cache. And I think that was it. I think we left out questions.
Remember, good questions get good shirts.
What if SCN is missing?
Say again, sorry.
Let's say you're saying you're ordering by SCN. What if SCN is missing?
SCN is always there. If you set up, it should
Why
always
are you
be.
capturing like all? Let's say you have a big database. You have your payments table, and there are some unrelated tables. You want to get the SCNs for some unrelated tables as well?
No, so you define upfront as part of the mapping, as part of the analysis of what you need from each payment system. So each payment system is different, like I said, has a different set of tables. We would define that, payment system A uses table X, Y, and Z, and then from a CRX perspective, we can actually define that, because CRX is listening to the reader, it's getting every change on that database, pretty much. So you can define what to filter out and what to keep. So you can say,
SCM by itself, it doesn't give you a set of tables, right?
SCM will give you the individual commit for that particular transaction.
Yeah,
right?
so you might not get kind of ordered SCMs. You may get 1, 2, 2, and 4. You may not get 3, right?
No, but it's still within the tables that we're interested in. We'll still have an order. That.
Yeah, you will have order, but you don't know. Should you wait for 3 or should you order it right now, right?
It's always increasing.
It's always increasing. Yeah, I mean, there's a general rule that you just be increasing. You don't know
It will be
increasing.
You're saying at this point in time we sort it, but you don't know. Maybe that number somehow will come later, right?
I mean, as long as it's ordered and we're not going to a lower number, that's what ensures that I have integrity in HBase.
Remember that we read transactions from the reader log itself. So in a reader log, we always read the tail, the last point of transaction. So what has been already read and published, it is there. After that, if you have another transaction, the SCM will be always higher. Before SCM depends on a
Okay,
time.
let's take it offline.
Before we take the next question, I want to remind everybody we are giving away 2, not 1, but 2 different smartwatches to 2 different people. In order to win that, you got to put your business card in here. If anyone didn't have a chance, I see hands up. Can you just pass that back to all the people?
Can I give you a piece of paper?
Yes. Oh, I should give you a piece of paper? You got a link over there? You have a question? Yeah.
Supposing the scenario if the Kafka or MongoDB is down and the legacy database is still working and there is inconsistent in the database, after 10 minutes, how would the...
So we continue to capture changes, and it depends if you have enough. Remember, CRX is running on an individual VM or physical server. So if you allocate enough space to this VM, they are capable to capture and accumulate to a certain extent, of course, the amount of changes until your Kafka or your MongoDB is back.
And if it's very bad, then you have to do the entire migration of, right?
Yeah, no,
It's
so
very inconsistent.
Yeah, so what we've, that example came up, right, so we have that issue come up. So what we've done is, one is, we have certain mandates from the source system. So the source system, we say you have to keep a minimum of 12-hour redo logs or archive logs. So we have a minimum set that you know that you can always go back to for your redo and archive. And then CR actually sort of transparently can read between switch between the reader and the archive. And then the other part of it is, say you have some fatal failure, the system's totally down. We have a concept of a recovery stream. So in parallel, when the database comes back up, you can continue ingesting from where you left off. And then you can keep a parallel recovery stream with an SCN range that will define a min and a max of where you left off. So you can then make up for that downtime.
What's the...
No, I'm sorry, I was pointing at her.
Yeah.
Sorry.
Okay, I have a question to Michael. When you write into S3 bucket, is it just JSON format always, or you can write in Parquet, Aura?
Currently, it is a JSON,
Okay.
but we are thinking to a Parquet format. Right? Currently, it is a JSON.
Yeah, the guy who kind of stopped this
Yeah,
question.
for
Sorry.
the CDC, if you think about non-intrusive, if the source, you don't have the access to the logs, so you just issue a SQL based on some kind of timestamp, because you need to capture the change, right?
Yeah, that's always through the log. You have to have access to the log.
You always have the
Yeah.
access to the log, right?
Yeah.
Thank you. You don't have a case that you don't have access to the log.
No, that's the default. You do need to, so it runs like any other replication tool. So if you're using Golden Gate or if you're using some other replication, you need access to the underlying files.
Yeah, but let's say if you have a source is managed by a third party, and for example, like say SAP, then there's no way you can access their logs.
Yeah, I mean that I wouldn't know.
Okay.
Yeah, so you said that we have a timestamp issue with HBase, right? So how do you resolve that?
Yeah, so that's what I'm saying. We were using the SCN
Okay.
to replace the time. So instead of the timestamp, using the SCN.
Oh, from your,
Do you have a DR for your system?
DR for the
DR for recovery.
yeah, for the cluster.
Yeah.
Yeah, we have a DR.
So it's like automatic preload, or you have to do manual?
Yeah, I mean, right now, so the issue is that we're using Cloudera Kafka, so it comes with a tool called Mirror Maker for the Kafka replication. We're actually switching to Confluent Kafka, which has a much better replication process. But yeah, we have it, but there is a downtime in terms of switching over to DR and switching that to queues.
He's got it right.
Did you ever implement that solution with using S3 in production? Since I think the cost of bandwidth should be of concern if you have like million transactions per hour. And when you need to retrieve that, they charge for downloads. AWS.
Oh, AWS. Yeah, we're not using AWS. This is in on-prem solution.
Yeah.
However, we've just done a pilot with AWS using EMR for the Hadoop side of it, the Spark side of it, the Spark and HBase side of it, and using Kafka as well. So we're in pilot mode, but yeah, we'll see how that develops from a process.
Question actually. Instead of Kafka, would you have been able to use something like Postgres? Because Postgres supports both non-SQL with the 9.4 release. You could do both, right? Either or.
Yeah.
Why would SQL would have worked as well in this scenario, or was there a basic reasoning you needed the PubSub architecture to make this work in your specific scenario? That's why you didn't use Postgres for this scenario.
Yeah, for our payment scenario, we're talking of just the volume of payments flowing in from. So it's a lot of different payment systems. So within their systems, they have they're using these SQL databases, right? But when you accumulate all that payment data together, it really becomes a big data solution rather than a SQL, a sort of a standard SQL solution. So in terms of scale to volume and then velocity of processing into Kafka using Spark to process that, that was really the only viable solution to be able to take that kind of data load and then make it available in near real time to get processed and be available for end users.
Oh, because of the out of order, and it becomes unstructured in a way actually, the way data is coming at the system essentially, right? There's multiple.
Yeah, and it's just the volume and
Volume
velocity.
and
Volume and velocity.
Absolutely. Okay, thank you.
We got time for one more question?
Yeah. I think two of them got answered is when you, so my original question was when you don't have a primary key in the source system, and then you are doing an updates. So you are using a database internal key somewhere to do the update into, if you want to do an update into the destination system. Like how do you tag like the insert and update if the source system doesn't have a unique or primary key? So,
For Kafka targets or any journal targets, primary key is not required actually.
no.
For HBase, it is a requirement. You must have. But for Kafka, we transform every command into the insert at the end.
Yes, no, I'm talking about, let's say, there is a RDBMS here, a source system, and RDBMS as a destination also. And that you are replicating
Yeah.
the non-primary key, like non-unique key data. So then if the system adds identifier, then where it tracks that identifier.
So for any end state, like HBase or even Postgres or a SQL target that is should be exact replica, any unique key identifier is a must.
Okay.
By the way, it can be some application unique key, but not
Yeah,
something that can be
business.
found in Oracle. Maybe you have some application unique combination of columns
Okay.
that you can define. We provide you an interface to define some unique identifier combination.
So business.
Yes, the business.
Yeah, and the second question was just like, how do I map if I have to transform some of the records to something else or a join? So is there a separate configuration UI where I can define the streams and like remap them, or there are only two outputs from your product perspective? One is rotation and one is that the log.
Okay. Basic transformation can be done. using CR8, but usually we leave this to the next part, to the processing part. And this is exactly how it works.
Yeah, so like you have to write something on your Kafka output stream
Yeah,
before you
this is-
send it to the destination.
Yeah, so I mean, I can give you an example, right? So if you think about it, all these different systems, they have their own unique key. So for example, if I have a payment, let's give you an example, we have a payment that's going from New York to London, right? So in the New York system, it's a totally separate system. They have their own payment transaction key, right? Now the London system has their own payment transaction key. So when I bring this data in, I need a third surrogate key, which is basically identifies both and can link both of them, and then I create a composite,
Yeah,
and
so-
then I can track that.
So alias
But you have to create them.
create
Site
post
ID.
Kafka.
Yes. Okay, we got time for just one more question.
Just want to touch base on the geographic location, like all these 50 data sources, they're all not co-located actually, but they're all spread across.
Yeah, you're global. Yeah, Asia, Latin America, North America, Europe.
Did you place DBSH? They're all spread across.
So the way, the good question. So the way we do the way we do the CR8 virtual machine, it's actually a virtual machine. We try and co-locate it in the same data center as the source database. So if my source database is in Singapore, I'll have the VM for DBSH in Singapore. However, my cluster is in North America. My big data cluster is in North America.
So every data source has its own version of the DBSH.
They have a VM that can either you can share that can be shared or depending on the
Same location, same data.
within the same. We try and keep it in the same place.
Okay, that's all the time we have for Q&A, but our speakers will be here for one-on-one questions right after our raffle. I want to give a great big round of applause to all of our wonderful speakers. All right, we are going to start the raffle now. Has everyone had a chance to drop their card in? Last chance. There's 2 winners in this room. All right, can I ask you to mix them all up? Can I ask you, look that way and pull one card out. Reach in and grab a card.
All right.
All right, read it aloud.
Jason Horn?
Jason Horn. All right, he's winner number 1. There's someone else in this room who's a winner, though. Hang on. Can I ask you to look that way, reach in and pull out another card? All right, read that out loud. Leonid Saplin. All right, congratulations. Come on up to have your questions towards the speakers now. Thank you all for coming. Thank you very much. Congratulations.